B. Begin at the absolute foundation of mathematical thought. The set. A set is not merely a collection. It is an abstract container of distinct objects, defined solely by the condition of membership. In advanced set theory, we move past the intuition of bags of things to the concept of externality. This principle dictates that two sets are identical if, and only if, they share the exact same elements. It does not matter how those elements are arranged or how many times they are described. If the membership is the same, the identity is absolute. This allows us to build the entire universe of mathematics from the most basic building block imaginable, the empty set, a void that contains nothing, yet serves as the starting point for all existence. Naive set theory suggested that any property could define a set. Bertrand Russell exposed a fatal flaw. Consider the set of all sets that do not contain themselves as a member. If this set contains itself, then by its own definition, it must not. This logical explosion proved that sets cannot be formed arbitrarily. This crisis forced mathematicians to move away from intuition and toward a strict axiomatic framework. We realized that the collection of all things is not a set, but a proper class, a category too large to obey the standard rules of mathematical membership. 2. Resolve the paradoxes of the past. The Zermelo-Fraenkel Axioms were established as the rigorous constitution of mathematics. These 9 rules dictate exactly how sets can be born. They ensure that we can only build new sets from existing ones, preventing the self-referential loops that broke earlier systems. From the axiom of pairing, which lets us create a set from 2 objects, to the axiom of union, which merges collections, these rules provide a safe environment for infinite exploration. When we add the controversial axiom of choice, we arrive at ZFC, the standard foundation used by almost every mathematician today. It is a world where every object is a set, and every set is built from the void. Consider any set. The power set is the collection of every possible subset that can be formed from it, including the empty set and the set itself. Georg Cantor provided one of the most profound proofs in history. The power set of any set always has a strictly greater cardinality, or size, than the original set. Even for an infinite set, its power set represents a larger infinity. This implies that there is no largest infinity. We can always take a power set to climb higher into the transfinite hierarchy. If we start with the natural numbers and repeatedly take the power set, we create a ladder of infinities that grows in complexity and scale, stretching toward an unreachable horizon of pure logic. The axiom of choice. It's perhaps the most debated rule in the mathematical canon. It states that if you have a collection of known empty bins, you can always pick exactly one item from each bin to form a new set. For a finite number of bins, this is trivial. For an infinite number, however, it requires the existence of a choice function that may have no descriptive rule. While it seems harmless, it is the engine behind many non-intuitive theorems. It allows us to compare the sizes of any 2 sets and ensures that every vector space has a basis. Yet, it also allows for the paradoxical doubling of spheres, proving that in the infinite realm, the ability to choose is a formidable power. The Banach-Tarski theorem proves that a solid 3-dimensional ball can be decomposed into a finite number of pieces. Specifically, 5 wits can then be rotated and reassembled to form 2 identical balls, each the same size as the original. No stretching or adding of material occurs. This is possible because the pieces used are non-measurable sets. In the finite world, counting is simple. In the infinite world, we use cardinality. The smallest infinite size is known as Aleph null, representing the set of all natural numbers, 0, 1, 2, and so on. Any set that can be put into a one-to-one correspondence with the natural numbers is called countably infinite. Surprisingly, this includes the set of all integers, and even the set of all rational numbers, or fractions. So, how do we prove that some infinities are bigger than others? Cantor used a brilliant diagonal method. Imagine trying to list every real number between 0 and 1 in an infinite table. We can construct a new number by taking the first decimal digit of the first number, the second of the second, and so on, and changing each digit. This new diagonal number is guaranteed to be different from every number on the list because it differs from each at least one position. Since this number exists, but is not on our complete list, we have reached a contradiction. This proves that the real numbers are uncountable, and their infinity is of a strictly higher order than that of the natural numbers. Is there an infinity in between them? This question is known as the Continuum Hypothesis. Georg Cantor spent his later years trying to prove that no such intermediate size exists. In a shocking twist for modern logic, it was discovered that the Continuum Hypothesis is undecidable within our standard system of axioms. You can assume it is true, or you can assume it is false, and the rest of mathematics remains perfectly consistent. This suggests that our fundamental rules do not fully describe the nature of reality, leaving a mysterious gap in our understanding of the infinite landscape. While cardinal numbers measure how many, ordinal numbers describe order. Once we count through every natural number, we reach the first transfinite ordinal, denoted by the Greek letter omega. But we don't stop there. We can have omega plus 1, omega plus 2, and eventually omega times 2. This is not about the size of the set, but the shape of its arrangement. Ordinals allow us to count into and beyond infinity. They provide the framework for Transfinite induction, a method used to prove that a property holds for an entire infinite sequence, and then for every sequence that follows it, stretching across an endless horizon of nested, ordered structures that define the spine of the set-theoretic universe. Nay, in the realm of the infinite, the standard rules of addition and multiplication are transformed by the law of absorption. When we add a finite number to an infinite cardinal, such as Ordinal, the result remains Ordinal. Even multiplying an infinite cardinal by itself, representing the set of all pairs of natural numbers, does not increase its size. The larger infinity simply absorbs the smaller one. Standard mathematical induction allows us to prove a property for all natural numbers by showing it holds for 0 and then for the next number in sequence. Transfinite induction extends this power across the entire ordinal hierarchy. To prove a statement for every ordinal, we must verify it for the base case of 0 for every successor ordinal that follows another, and crucially, for every limit ordinal. A limit ordinal, like omega, has no immediate predecessor. It is the boundary reached after an entire, infinite sequence. By proving the property holds at these jump points, we can climb the ladder of ordinals indefinitely, ensuring our mathematical truths remain valid even as we pass through countless layers of the infinite. Bewildering principle asserts that every set 2, no matter how chaotic or dense, can be arranged in a sequence where every non-empty subset has a definitive first or least element. While this is intuitive for counting numbers, it is mind-bending for the real numbers, where no smallest positive value normally exists. This principle is logically equivalent to the Axiom of Choice and Zorn's lemma. Zorn's lemma is a powerful tool used by mathematicians to prove the existence of maximal structures, such as a basis for an infinite-dimensional vector space. It states that if every chain in a partially ordered set has an upper bound, then the set contains at least one maximal element, providing a bridge between local order and global existence, V. We can visualize the entire collection of sets as a vast, unfolding V-shaped hierarchy known as the von Neumann universe. We begin at the base with the empty set, the only object that exists without prior parts. We then systematically build stages or ranks. Each new rank consists of the power set of all previous ranks combined. At stage 1, we have the set containing the empty set. At stage 2, we have all possible combinations of the previous stage. This recursive process continues through all ordinal numbers, creating a skyscraper of sets. In this model, every mathematical object from integers to complex functions is eventually found at a specific rank, showing that all of mathematics is essentially set-sized furniture in a singular infinite house. Within the von Neumann universe, the axiom of foundation acts as a cosmic speed limit. It dictates that every non-empty set must contain an element that is disjoint from the set itself. This rule forbids a set from containing itself, either directly or through a circular chain of membership. It ensures that the membership relation is well-founded, meaning if you trace the contents of a set downward, you will always eventually hit the bedrock of the empty set. This prevents the logical ghosts of infinite descent and circular paradoxes. Foundation ensures that the hierarchy of sets is a sturdy one-way street, where every complex object can be traced back to the simple, silent void of the beginning, or, as we climb higher into the transfinite, we encounter inaccessible cardinals. These are infinities so massive they cannot be reached from smaller infinities, using the standard tools of addition, multiplication, or even power sets. To reach an inaccessible cardinal, you cannot simply build up to it. You must assume its existence as a new starting point. These cardinals are the giants of set theory. Their existence cannot be proven within the standard ZFC axioms, making them large cardinal axioms. If an inaccessible cardinal exists, it acts as a miniature universe, satisfying all the rules of set theory within itself. They represent the first major step into the unreachable peaks of the mathematical landscape. Beyond the inaccessible lie the measurable cardinals. Defined by a sophisticated concept called a non-trivial capo-complete ultrafilter. In simpler terms, a measurable cardinal is so large that we can define a consistent way to measure its subsets, assigning them a value of large or small without falling into contradictions. The existence of a measurable cardinal has profound ripple effects downward on smaller sets. For instance, if measurable cardinals exist, it proves that the universe of sets is not constructible in the simplest way possible. These cardinals introduce a level of richness and complexity to the real number line that is invisible to those who only look at the basic axioms of arithmetic.